Good morning to everyone. Dear guests, dear participants, it's my great pleasure to introduce to all of you our keynote speaker, Mr. Gerard Assayag. Gerard is the founder in 1992 and head of the Music Representation Research Group at the ICMC in Paris. He is also research director of the Science and Technology of Music and Sound at CNRS. His research domain is on music representation, which more specifically includes computer language paradigms, machine learning, constraints and visual programming, computational musicology, music modeling, and finally computer-assisted composition. Gerard developed the first ICMC environment for sport-oriented computer-assisted composition, and in 1998 he created with Carlos Agon the well-known open music programming environment, which is currently used by numerous composers and musicologists around the world. Ladies and gentlemen, please enjoy the presentation of Gerard Assayag on creative symbolic interaction.
Thank you very much. I would first like to thank very warmly the organizers of ICMC and the SMC 2014, and specifically Anastasia, who did a wonderful job in organizing this huge and beautiful event. Thank you for the invitation. So I'm going to talk about symbolic interaction in the context of creating creative agents that have enough machine musicianship to be able to play along with human and improvise with human. So basically what you need at the current time, an agent has to be able to evaluate the past, to analyze the present, the incoming events, and to have some anticipation strategy in order to build up the future. A few remarks. You are not necessarily linked to hard real time for this kind of intelligent behavior, because it takes time to come to a decision, even for human. It can take milliseconds, hundreds of milliseconds, and sometimes seconds, and sometimes minutes. It involves time and memory at different scales, just as in music composition. So the approach will be halfway between composition and improvisation. And a general remark is that it cannot be always fully apprehended by mainstream, traditional signal processing, even processing technology. You have to get into some different things in order to be able to emulate intelligent behaviors. It's not only a matter of processing streams. So you have to bring in synergy a combination of means which are, I will detail this during the talk: machine listening, machine learning, stylistic simulation, symbolic music representation and construction. And you have to make all these means work together, to cooperate and sometimes to compete. So we're aiming at a multi-level machine musicianship, smart musical memory, with some discovery and generative skills contributing to the emergence of some creativity in the machine. So I will specifically describe an instance of such a system. I've been working with friends during many years, which is called OMAX, which had during the past years many siblings called Somax, Amphotech, Mini, Native, Alien, in many different subjects, not only IRCAM. So it's an idea that kind of spread out. So we'll have some cooperation between real-time audio. I already said that music representation and formal knowledge, and we want to be able to learn and preamplify during the concert time, to be able to just come up on stage, learn from musicians, even if the memory is empty and naive at the beginning of the concert, and be able to hook up to what the musicians are doing and play some significant music, be pertinent. And this will be the last part of the work, very recent work. We want to be able to connect to instant contextual listening. we won't be able to connect instant contextual listening, that is, understanding what the musician is just doing at the present time, with vast musical memory, that is corpus-based knowledge that you have learned offline. So be able to connect very short-term memory with very long-term memory, including cultural memory. So I call the term symbolic interaction, just as a way to say that interaction is not only a matter of signal processing, of reactive system, or event handling and event processing. It has to connect to some higher level representation that are usually used for composition rather than for interaction. So the idea is to bring together the advantages of different worlds. Interactive real-time computing on one side and intelligent content level analysis, semantic processing, formalization of music on the other side. So bring this together with a decision-making paradigm in order to be able to make decisions step after step. Either by relating to the long-term memory, that is related to a neural structure that you have and that define the musical context, or take instant decision and jump to an unexpected place in the structure, which is really the improvised act that humans do so well and that is difficult to do in a autonomous way with a machine. Of course, you can do it at random, but it's not the purpose. So, we're aiming at liveliness in computer system, which is precisely this mixture of deterministic and unexpected or improvised behaviors, as you have in living organism. So just to quote what I said yesterday in the Plato talk, the Platonic rhizome, music is a synthesis of time from the dialectics, to put it in a kind of philosophical terms, from the dialectics of immanent forms and transcendent causality. What is immanent form? When you are formalizing music, you have a bird's eye view over the whole structure, and it is kind of immanent. When you are into reactive system, interactive system, you are in causalities. Each new event conditions causally the next event, and is external to it. This is what philosophers talk about. Transcendent because it is external. Just a reference to this beautiful evening we had yesterday in the Plato Academia. So I will, from now, zoom in from a very brief description of what we are doing at ICMC in the lab, SCMS. SCMS is for Science and Technology of Music and Sound. Then inviting music representation, and then in my specific work, with some recent and not so recent development of this work. So, most of you know IRCAP, so I won't detail this. It was funded by Carboulez in the 70s, and it's a nice place where you have musicians and scientific and tech people working together. And the lab inside IRCAP is associated to the Research and Development Department at IRCAP, and it gathers researchers in engineers, which are structures in teams. So there is a structuration in themes. We have four main research axes, which are modelization, interaction, representation and languages, and foundation and theory, ignition and musicology. And the themes are distributed around this thematic division. So my team music representation, we see it here, and we have software for composition, for orchestration, for improvisation, performance, for following, and also a strong activity in mathematics and music that was developed in the workshop. So we have an analysis synthesis team which is working in sound analysis and synthesis with physical models, signal models, work on voice and many other topics. We have an interaction team which is concerned by gesture capture and modelization and mapping to sound and musical structure. We have acoustics team which deals with space, acoustical space, acoustical instruments and acoustical minds, so to speak, that is perception and cognition of sound in space. And a musicological team which deals with scores and music analysis and musicology of contemporary music. IRCAM puts a lot of software, so I have circled here software that are related to music representation, and I was I will specifically talk a little bit about open music and much more about OMAX and research, of course, that's behind it. So this is the research themes in the music representation team. So we have programming paradigms, computational musicology, symbolic interaction, which I will talk a great deal today, and symbol-to-signal articulation. And these are the PhDs that have been conducted in the team. So since the birth of music representation, which is in 92, we had around 30-35 PhD works hosted by the team. So we're going from the past to the present, and I have put little stars to the PhD work that have contributed to this symbolic interaction things I'm going to talk about today. Also a lot of publishing activity, books collection, and co-creation with colleagues from all the world of the mathematics and music journal that you've probably heard about. So this is open music, as described in books that we edited a few years ago, with works from composers that showing the high diversity of this software. So open music is really our music composition, computer-assisted composition environment, and it's purely graphical, just as the Max software, except it's more designed for offline works, offline designing. Works of designing musical structures and scores. So here are a few example screenshots of open music. And the basic thing, the concepts in open music that I designed with Carlos Agon years ago. The idea is writing form in time. Remember, music is a synthesis of time in a pseudo-Deleuze quote. It's the idea to have a series of couple of opposition. So it's a reflexive visual programming environment, multi-paradigm, that is, you can do functional programming, imperative programming, logical programming, and many other things. And you have a series of duality. You have the duality between structure, that is form, that is this immanent thing, and process, that is computing in time, and causality. So it's easy to mix them together in open music. You have this duality between deep level and surface level, deep level of computational description of things, and surface level of editing surface musical object like scores or signal. And it's easy again to go from one implementation to another, which are summed up in the duality between signal level representation and symbolic level representation. Here is just a short animation of using the opening. You have patches like in Max, you have a visual program which represents the computational structure, and then you have maquettes which are computational structure in time, so you have a time axis, so you can take a patch and drag it into a maquette and it becomes a musical object that deploys in time. And then you can look at this object with a computational view, that is the structure, the formal structure out of time, or the software structure, that is a musical object. Here is a signal, it is score. And then you can take this maquette, which becomes a single object, and drag it into another maquette building up hierarchical structures of musical form. And then this very complex structures can become again a single point in the computation, so you drag it again into a patch, and it becomes a single source of computation. So the loop is closed, and you can go from computation structures to time structures to surface representation and back to computation. And it's very practical, and it's in the position like this, and use it a lot. So now zooming in to the OMAX and symbolic interaction project, a tribute to many people, many wonderful people who contributed to this idea and this environment, and you can actually use it in musical setups. So what is it all about? The initial idea was to virtualize the musician, so be able to listen to a musician, model it, so to speak, clone it, so to speak, and play with this clone in order to be able to interact with the musician. And then the idea would be to go beyond the idea of clone and to create, that is, inventing possibility for this agent context is a live music performance. The data are audio streams that arrive in real time. The model is a file model that captures the musical logics underlying the files and the musical streams, and it outputs musical sequences, hopefully with the same logics and with the same sound, if this is what you want, or with different sound if you want to synthesize your sounds. But the idea is to mimic the behavior of the musician. So the resulting situation is human musician playing freely along with the virtual one and creating kind of dialogue. That was the initial setup. That was very inspiring for us and helped us to design the first prototypes. So I tried to capture this idea in a kind of epistemological setup in order to understand what we are doing. So it's pseudo-cognitive because I'm not the person from cognitive science or perceptual studies, but it's cognitively inspired. This is what I imagine that's actually happening in the world and that we are trying to simulate. So suppose you have a musician who is improvising alone with fellow musician. He has a memory, he has learned things in his life, and these things are evoked in his improvisation. In general, information doesn't come from nothing. So it's often reacting of things that you have in memory, maybe combined in a different way. This is the evocation relation. And the musician is listening. There's a listening relation. He or she is listening to other musicians and listening to him or herself, right? Because when an improviser has to have this kind of loop, listening to what he or she is producing in order to correct, implement. Okay, so we have this first. And then all these images, that is the current context of the musical setup, the musical improvisation, the music that is produced by the musician, regress in time, and in memory, because all this is memorized by the and creates memory images of all this information. So this is the memorizing or modeling relationships, because when you are memorizing, you are also compressing information. It's modeling this. And so you have this double loop of self-listening and listening from what's coming from this virtual past. So the idea is that Omas redefies, using here a term of jargon, redefies, which means materialize this abstract thing and try to emulate it as an inspiration to the musician. So you see there are plenty of levels here because there is a natural phenomenon of double loop in the musical situation, and then you have a software which is kind of verifying this very situation, and you have to interact with it. So you come you're kind of in a very recursive situation. But it is, I think, what music and specifically improvisation is about. So we began the research, this idea on compression, and that was pretty much inspired by Kouroupetroglou, a fellow researcher with San Diego University. It was shown that finding the optimal behavior of rational agents is equivalent to compressing its observations. It's better to do that. The proof applies to enable seeking agent in any unknown environment which can be simulated by a computer. Another way to put it, there is a close connection between machine learning and compression. A system that predicts the posterior probabilities of a sequence given its entire history can be used for optimal data compression, while an optimal compressor can be used for universal prediction. So the relations can be reversed. If you can do universal prediction, then you can generate it. So compressing is a way of modeling that helps you to generate things. So the very first prototypes were based on the very well-known compressor called the L-selected inclusive compressor. I take a sequence and builds up a kind of dictionary of segments into this sequence. I won't detail, but you can represent this as a tree. And in this tree, Some parts will act as a context, for instance here we have the context AB that appears in the sequence, and other parts will act as a prediction, which is if you have the context AB, then you could predict that it can be followed by A or C. Very close to the Markov chains, but you can go beyond the Markov models with this kind of things. So this is optimal coding and universal prediction. I won't detail this, but it has the good properties. It means that when you're making such devices, it's equivalent to having not a single Markov machine, but an infinite number, a virtually infinite number of Markov machines that adaptively converge to model your sequence. So you're not linked to a certain Markov order, but you have just as many orders as the sequence needs, and in an optimal fashion in order to model and order for the system to generate movement. So graphically, it means that if you have this sequence and you notice that you have a pattern repetition, you can use this information to build up new form by predicting from the end of the pattern to the end of another similar pattern. And then you have a form that emerges that was not in the initial sequence, but that's interesting because it has the statistical properties. Okay. This is kind of well known. So here are a few very early results. Years ago, so we were just modeling MIDI files and trying to generate pseudo music. So for instance, a generation in the style of Bach, in the style of Charlie Parker with an ugly mix. And then we moved to leading musician and working a lot with Gerard Assayag, famous French jazz player. Here's an extract of the real one, playing a concert in Bob style, and then the model playing reconstruction. And construction with different sound. So 20 minutes recording of an aruba, and the model can play forever and ever, and always changing. It changes the average every 2-3 seconds the path, so taking different options than the original. Okay. An example in audio, so exactly the same idea, but now we have some simple machine listening. Trying to listen to the audio, to segment the audio, to extract the pitch, and then build up the model the same way with MIDI information. And then getting back to the audio in order to remount, to edit the audio, in order to build up the new sequence. So this is straight from the records from Jacob Astorius playing the improvisation on Charlie Parker, and the reconstruction by the software. So very different improvisation with exactly the same style. We had some problem at the time with the reconstruction of the audio, so there's some distortion in the signal. So we have this general framework of double loop of what we call stylistic reinjection system, because it is between the present time and the virtual past. What we need now is a system of representation in order to be able to model what's happening actually in the improvisation. And we must have some perceptual and generative strategies in order to be able to build up in an interaction setup. Because up to now, there's no interaction, it's just modeling and generating. This is very classic. So, a strategy. We need a strategy for browsing the model and generating new sequences. So, to sum up, we have to have some efficient machine listening scheme that will be perception aware and be able to segment the sound signal into musical units. Distributed on some geometry in order to be able to cluster things and to infer symbols as elements of a musical alphabet. we cannot stay at the signal level, we have to explore the high-level unit, label them as a part of an alphabet. And this will be cognition, ideally cognition aware. So you have to discover an alphabet structure according to the screen. You have to learn this stylistically into some formal structure. And then you want to do a strategy for generating and rendering new sequences. You want to do this in real time, interacting with the musician. So the three processes have to happen in a parallel or concurrent way, cooperate and compete. So as for listening, for simple monogistic signal, we use pitch following software like there is a representation of yin frequency following and qualification from which you can extract clean note insets and outsets. And if we're dealing with an arbitrarily index signal, then we have to go to a spectrum and be able to extract units that are meaningful spectrally and timbrally. So we do this with the MFCCs, many frequency classical applications, that give you some vectors, multi-scale vectors that represent the spectral shape. And we do some adaptive quantization of these vectors. There's some local group averaging on some geometry, some Euclidean geometry, and the precursor then can extract those and call them signals. So every time you have such clean information, you have a musical unit that is cut for the segmented from the signal and labeled, and will be able to recognize if it becomes a bit awful with something very silent. So for pitch, it's quite easy, and for timbre, depend a lot on the structure of the signal. When it's purely MIDI, then it's there's a slicing mechanism where you slice vertically polyphonic slices every time you have the burst of left of an event. And you keep all this information. For instance, you keep the information that an event has been sliced, but continues in the next slice. So when you will be generating new sequences, you'll be able to regenerate the polyphonic structure. Okay, the formal learning structure is a structure that we found in the literature. It was not in the literature, it was the formal language literature, and also the bioinformatics literature. It's a structure called a factor oracle, which is a kind of graph, which is this way, incrementally by bringing a sequence from symbols from left to right. I will not detail that, so we just give the interesting properties that we find in this structure. So this is a factor oracle, representing a sequence of symbol A to B from left to right. So you have two sets of arrows, forward arrows and backward arrows. And forward arrows model a factor, which means that this is an automaton that recognizes factors of a word, the sub-words of a word. And the backward arrows have a very interesting structure. They were used in the original algorithm as construction names, but actually they are the ones that we're interested in because they give this structure, which is a roadmap into the pattern organization of the sequence. So every backward or suffix link connects two patterns, two similar patterns, exactly so two exactly relative patterns in the formal alphabet case, but two similar patterns if you have functions that can detect similarities. So you see that you have this connection from a pattern with its first occurrence starting at the beginning. And this arrow structures actually can be deployed into a tree structure. If you take one of these arrows and put it up, you get a tree, you get a forest of different trees. Every tree completely explains the genealogy of the pattern. See? So this pattern is connected with this one, but then also with this one, and then you have a different pattern on the left of this one, but then the longer pattern, which is dark red and gray, itself is repeated in another part of the sequence. And here you have the same information with a numerous sequence here, and you see that the numbers are the lengths of the pattern, and you see that the trees are ordered in lengths from root to node and from left to right if you want to have this dimension, which helps you to achieve a lot of optimization when parsing the tree. In order, for instance, you are generating this thing, and you would like to instantly all the other parts in the musical sequence with a similar pattern, and we find them very easily in the tree because of optimizations due to the fact that it is observed. So this is the whole structure. Here, an example by Archapent. Archapent in his thesis and several papers also use this factor oracle similarity structure, but with a different geometry. So it's not a Euclidean geometry anymore. It's an information geometry. I will not detail this. But apart from the geometry, you have here sound signal, which is in this case the Beethoven's first piano sonata, played by Buddha. It's an ancient recording, so it's very noisy. And here is the factor oracle that recognizes different states cut into this sequence. And it's interesting to see that it's not so difficult to reconstruct the formal structure of the sequence. So you see you have here layers corresponding to segments which explain the thematic structure of the sequence. So it's a good model. It's a model that is powerful and that is very friendly and computationally. So you can use it in a construction set. Another way to look at this model is that it's a correlation matrix which is sparse and which is given to you instantly as a sparse structure instead of constructing a correlation matrix and then locating existing substructures in the matrix. When building incrementally factor oracle, you build directly the sparse structure. So the correlation matrix, so it gives you the roadmap into the things. Okay, this is just another representation with arches. This is a representation that you have in the software organized that connects different parts of the sequence with different colors and different thickness of the arches, which represent time. So, for instance, if the similarity criteria is pitch, then the patterns can be equivalent in pitch, but with different time durations. So, the thickness of the arches tells you if the music is accelerating or slowing down, etc. This is an improvisation by Cecilia, where we see that this kind of representation can also be musical analysis and signature of improvisation or of any musical sequence. So we give a few indications on how to listen and how to learn a formal model. Now we have to generate. So this is the general navigation heuristics on top of this model. So this is the factor oracle. And suppose that you have generated so far this sequence by just reading and so replicating the music that you have done. So you have not invented anything. Then you would like to jump to another place and you would like to find a similar context in order to jump to the same context. So the idea is to look a little bit in the future of the sequence and to evaluate for each point all the possible jump candidates which are represented under the form of a tree. Remember, these are the tree. They are organized into the tree. So you do this person on the window in the future, and suppose that you find here a tree that's interesting with a part of this tree that connects to the states. It means that you have a very good complex here, which is duplicated here, and then you have it legitimates the idea of jumping from here to here. So first you move to this part by continuing to replicate, and from here to jump. So you have a free switch way of recombining in real time the sequence that you are learning. Maybe, this is the overall architecture, but I won't detail. And now I will show a video recording of what's happening in the software in real time. So you have as input saxophone improvisation, and you will see the factor oracle building up in real time. So you will see links appearing as you find similarities between segments or subsequence of physical units. And the more it learns, the more information it finds. So let's go for instance, for instance here. So it's interesting because you see that it found pattern relationship between this location, and here, and here, etc. And it has also a very strong auto-similarity structure in this part of the music, but nothing in between. It doesn't related to this green pattern that is very strongly represented here and very strongly represented here. And you see that this is a very interesting musical analysis. You have a first thematic sequence, which is very similar, then different material, and then you are re-evoking, recapitulating, or re-evoking something that happened at the beginning. This is real-time music analysis. So it's easy from this to do higher level segmentation by just gathering and clustering all this pattern information. So you will see higher level segments appearing. So here we have a segment. Here we have another segment. It's different, so it's a different color. Because not many pattern relation between the segment and the segment. And if you go further, you see that you have a relation between this green bar and this green bar. So you are able to segment the sequence into higher level units and then relate them in one way or another. So this is also online musical analysis, but at a higher segment level. Then, once you have, remember that all these processes occur simultaneously. So as soon as you have begun to model something from the musician, you are able to play. So how does it play? It just navigates, as I said, with the story I showed, on this representation. So you can see a sort of computer improvisation on the same sequence, and you will see this red cursor moving along the factorial, and then jumping when it finds an interesting way to jump. And before it jumps, you will see a phantom cursor telling you the place where it's going to jump. Okay. Can you see the phantom? Not so much. So the red diamond is an attractor. So you put an attractor in order to tell the system, well, it would be good to get closer to that attractor, but still following the logics I explained, not jumping artificially, but following the sequential logic and finding paths toward this attractor. It's an interesting possibility. So you see, you jump to the attractor in a very natural and smooth way. It's really like if the musician was doing it, except it's a sequence that was never played with the musician. So now, one of the first examples of interaction. Here you have the musician playing and the system analyzing and hooking up almost immediately with the musician, and we see how the musician and the system co-adapt in a way. That was one of the first improvisation was organized, and the musician Fabricio Cassol from the improvisation group, Belgium group at La Moon, is actually discovering this software. It's the first time he plays with this software. So we have the time of adaptation, and it's very interesting. So I have sampled this, I recorded this experience and sampled a few parts in the session just to show the evolution. So at the beginning the system is very naive, it can only repeat things that the musician is playing, but then you will see that it becomes more and more, it becomes smarter and smarter. Musician, computer. Musician, computer. And of course, the experience was going to work on the skill of the musician. Played with it and it puts interesting Bernard is playing the piano, and Omax so in all this situation, the memory is empty at the beginning of the concert, and it's Omax playing only by learning on the fly. You're not obliged to do that. You could learn offline, maybe musical information and use it for the concert. But here, the challenge is to see what you're able to do by just learning on the fly. So, let me explain the idea. Suppose that here you have the MIDI representation of a musical sequence where you have a chorus line, a solo, and an accompaniment chorus behind the solo. So, and the solo is visible here in red, right? Can you see this? So you can analyze the solo exactly the same way we showed, but you have still this background information, this harmonic information, that you can use in order to annotate, to stamp all of the musical units with annotation, with labels, that gives you some additional information on what was happening at the time the chorus was played, what was happening in the background. In that case, the harmonic background, but it could be any kind of background, like a rhythmic background, or even external things such as this visual context. Whatever, you can stamp a context visual information. Here, for harmony, we do it using chromograms. So this works on the MIDI and the signal and the audio signals. There's no difference. So we're using chromograms with an echoic memory inspired by Toyenen and Krumann's model, which say that every time a note appears, its importance grows using this curve here. And when it stops, it doesn't disappear instantly in the memory. So there is a persistence in the memory of a trace of this information. So it decreases using this exponential. And then the chromogram is built up on this idea. So now here you have your memory model, just as I explained, with units separated and arrows linking units and giving patterns into patterns. And you have the live input. This is what the musician is doing. So if the musician is currently playing this brown unit here, then you are located somewhere in the memory. Yes. And you are wondering what next. And in that case, as a difference with the traditional Omax, you want to decide what next, depending on what the musician is playing. Okay, so you want to favor paths in the memory model that will bring you in a play that is similar to what the musician is just instantly playing. And by so doing, we are going to extend the accompaniment paradigm, but to something more general, something that works even in the case of pure improvisation. So you can decide to jump in a play that is significant with regard to what the musician is actually doing, or to a place which is significant with regard to the label, the context annotation that they extracted from the musician, as it can be mapped to the label, the context annotation, as it is associated to the states in the model. So in that case, what you are doing is that you are generating an event which might not be similar to what the musician is doing, but which will be linked to a certain context which is similar to the context of the musician. So just to give a very short example here, we have analyzed the famous Keith Jarrett concert. I'm sure all of you know this concert. It's pure improvisation. So we have analyzed the right hand in the context of the left hand. So right hand is the main information, but the left hand is the harmonic with this chromogram and echoic memory system, is the harmonic labeling of the left hand as it is learned. Then we have an agent who knows this corpus and can improvise, so to speak, the Keith Jarrett's right hand. Then we have another agent which plays anything, and from this anything we extract the same harmonic information, the same harmonic level. And we drive the improvisation of the first agent in order to be able to replicate the style of Keith Jarrett's right hand, but always staying in the harmonic context that is extracted from the inputs, right? And this is done for the harmonic annotation, and this is done also for the tempo and pulse annotation, so the right-hand improvisation will also keep in time with the input. So here we input, it's called Autumn in Köln because we input a jazz standard called Autumn in Paris. It's again usually modified because could work exactly the same with the audio files. And Laurent didn't do it with the audio files for stupid rights problems. So we input auto in Paris, and our model of his right hand improvises in a harmonically coherent and tempo coherent way on top of auto in Paris. Sorry. So we'll skip directly to the recent results. So I don't have time to talk about the imported system, but here it's about the same idea, but the case where you impose a scenario which is known in advance, and then it gives you information about the future that you can exploit. You can pre-index your memory in order to find good location that match in a very continuous way to what you find in the scenario. But I will jump to recent results in the memory activation scheme. So here you have the memory, which is the linear formal model. So this is what you learn actually. And then there is something coming from the context, from the environment. So for instance, suppose that in the environment, you listen to the information A. There is some A in your model here and here, so you're going to put a continuous peak of activation on top of this location. You're going to put this kind of Gaussian structure, which means that these are important places in the memory because you heard A, and these places in memory have a high level of activation, which is a very natural model. But then time passes. So this is the activation of your A state here. But at the next time instant, you will have a kind of persistence of this activation that moves a long time, that will be on B. And then at the next time unit, you will have a certain persistence of this activation that will be on C, and etc. In a continuous way with this exponential decrease. So, suppose you have A and you have this 2 activation. Next time, B is entering. So, you're going to activate B. But at this time, the A peak has moved to B. So, you have a very high peak because it sums up. Same thing for here for B. And here, you have the remaining activation of A here in D, because you had an A symbol here. And at the next time unit, there's the persistence of this A symbol. Same thing for C, and here's an animation of what's happening of the activation pattern in the memory. So what's happening here is that, again, we find this classical Markovian scheme, which tells us that if I heard ABC, okay, I have the pattern ABC here, so the peak of the activation is very high, so I could get in this place in the memory and then play E, okay? But I have also this, because I can look at all the peaks and have a distribution and choose my peaks, my interesting location memory with a distribution among those peaks. And then I have here this ADC. So I have heard ABC, and here I have a high peak at ADC. And if I continue starting from this location, it means that now I'm doing fuzzy pattern recognition in a very simple and natural way. And the way it really happens in real life, because we're not looking for exact repetition, but for similarity. So this is a very powerful model, and it helps in obtaining very much better musical results, especially considering, and this will be my last theoretical statement, and then I will just give you an example. Considering that you can listen to many different things in the input environment. For each audio input, you can listen to many different musical parameters, that is, a label annotations, and you can sum up into a global activation function. But the interesting thing is that you can listen to yourself. So while the system is playing, it can listen to itself and create the activation pattern in its sound memory of what it is playing and combine it by linear combination with the activation pattern of what's coming from the environment. And you can weight all this information. And this is very good because you can decide that the system is more oriented towards itself, that it's just generating what it learns, or directed toward the environment, just reacting instantly to what's happening in the environment, or any point in and so this is a major improvement. I will just tell you, just to finish, a video of a concert that we recorded in June at IRCAM during the open doors. And it's here, I guess. So I have 3 videos and I will be very short, except. First video, you will see saxophones playing, and Omas is improvising freely from memory he learned of jazz voicings in the style of Bill Evans. But it's free improvisation, purely free. Nothing is designed in advance between the musician and the computer. So it's. Next one. In that case, there's only a saxophonist. The system learns from the first performance, plays for a minute, the system learns, then creates a new entity, which is a clone, and the musician plays with this clone, and creates a second entity, which is a different clone, and the 3 listen one to each other. This is a new thing. The 2 clones listen one to each other and listen to the musician. So we have from time to time very interesting synchronization emerging.
control, because depending on what he plays, and you see that from time to time he launches this kind of call and the same reacts, because it's a very strong thing in the memory, so the two agents tend, but it's not always the case, but tend to go to this location in the memory. So the mission feels that he can, to a certain extent, control what the agents are doing. And just the last example, where you have an external corpus. So we learned the Klavierstück by Schoenberg, the Schoenberg Klavierstück. And the machine improvises on top of the Schoenberg Klavierstück, but the agent plays the Schoenberg Klavierstück, not literally, it improvises it, re-improvises the Schoenberg Klavierstück. The musician improvises on top of this. The system listens to the musician, creates a new clone of the musician, and then the three together, listening and again, everyone listening to the others, try to co-improvise. And at the end, the percussionist enters into the dance, but he's not modal, it's just a play. It happens. It's This is it. Thank you for your attention.
I would like to thank you very much, Gerard, for your this very, very interesting presentation. Thank you.
Thank you.
Gracias.